Speak of the devil, I didn't even know this was the next problem, but apparently it is the next problem. So what we're going to do is find the integral from -1 to 1 of the absolute value of x. And again, I want to remind you what the absolute value of x looks like. It looks like this right here. And so from -1, 0, and 1, this would be the point -1, 1, and this would be the point 1, 1, okay? And so what's the idea here is they're saying you should find the area of the blue piece, you should find the area of the green piece, and you should add them together. So let's see if we can do that. So what's the size of each of these? Well, the base of each of these triangles is 1. The height of each of these triangles is 1. And remember, so the area of the blue triangle, I'll just write it, area of the blue is going to be 1/2 times the base, which is 1, times the height, which is 1. So that gives us an area of 1/2. The area of the green, exact same shape, 1/2 times base, which is 1, times height, which is 1, so that's also 1/2. So to find the total area, we would add those two numbers together, 1/2 plus 1/2, and that would give us a total area of 1. So what did we do effectively on this problem? What we did was we broke this up into two separate integrals. We integrated the integral from -1 to 0 of the absolute value of x with respect to x, plus the integral from 0 to 1 of the absolute value of x dx. And the reason that we did that is because we can better define these functions on those intervals. This is the integral from -1 to 0 of, well, this function right here is -x. So we could have looked at this as -x with respect to x, plus the integral from 0 to 1 of, well, this function right here is the same as y equals x. So this one would have just been the integral from 0 to 1 of x dx. So taking the absolute value, breaking it up at a point in between the interval, in fact we broke it up at 0 was the one we broke up, gives us two simpler functions to integrate, which gave us our final answer. Okay? What are some other properties of definite integrals? Well, it's the same as the properties that we've seen for indefinite integrals, as well as the properties for derivatives, as well as the properties for limits. What can you do with constant multiples? Pull them out in front. What can you do with addition and subtraction? You can separate them, okay? So far we have some rules here. If the integrals are the same, a to a of f of x dx, as long as those are the same, we know that is equal to 0. Doesn't matter what the function is. Constants we can pull out front. Addition and subtraction we can separate. The only other one that we knew was the integral from a to b of f of x dx. You can break it up at any point, so this would be the integral from a to c of f of x dx, plus the integral, pick up where you left off, c to b of f of x dx. So that seems like all the rules that we have so far to play with. So let's look at this. It says evaluate the integral from 1 to 3 of -x squared plus 4x minus 3 with respect to x using each of the following values. It tells you the integral from 1 to 3 of x squared is 26/3. It tells you the integral from 1 to 3 of x is 4, and it tells you the integral from 1 to 3 of dx is 2. So what can we do? Because this is a definite integral, we treat it just like it's an indefinite integral using all the same rules. So we're going to separate this into 3 separate integrals. We're going to pull each of those constant multiples out in front. So let's see what we'd have. We'd have negative the integral from 1 to 3 of x squared dx, right? Then we'd have plus 4 times the integral from 1 to 3 of x dx. And then we'd have minus 3 times the integral from 1 to 3 of 1 dx, or just dx there, right? And now we can substitute in those values. We know the integral from 1 to 3 of x squared dx is 26/3. We know the integral from 1 to 3 of x dx is 4. And we know the integral from 1 to 3 of dx is 2. So what do we have here? We would have negative 26/3 plus 4 times 4 minus 3 times 2 Go ahead and put that into your calculator. I'll leave my answer as a fraction because it's in terms of thirds, so I'm getting a total answer of 4/3 here. Okay. So what's the next one say? It says if f and g are continuous on a closed interval and they're both positive, okay, so they both have to be non-negative above the x-axis. If f is smaller than g, then the following properties are true. First, the area of the region bounded by the graph of f and the x-axis must be non-negative. That's because it's all above the axis, right? Second, the area must be less than or equal to the region bounded by the graph of g. Okay, so what are we saying here? Let's just look at a visual right here. What if we had the interval from a to b? What if you have a function here, f of x, and you have a function that's always bigger than it, g of x? All it's saying is if we found the area from a to b of f of x, which would be that blue area, right? That has to be less than or equal to the area beneath g of x, which would be all shaded in green for you, that shaded green area right there. Okay, so that's all that is saying right there, and those two properties are generalized in the theorem on the next page.